work, power, and energy in rotational motion. Rotational motion. Okay, so the kinetic energy of a rotating object is found similarly to that of linear kinetic energy. And the equation for linear kinetic energy, as we already know, is half mv squared. And the linear speed of a rotating object depends on both the distance, or r initial, from the axis of rotation and the angular speed. And the angular speed in rotational motion is known as omega. So the equation we get is VI equals RI times omega. And the total kinetic energy of a rotating rigid object is the sum of the kinetic energy of all the individual parts. And so the kinetic energy equals the summation of K initial equals the summation of half mv squared. And since we already know that V equals R times omega, you can substitute that in to the equation, and you will have the summation of half m times Ri times omega squared. And the total kinetic energy of you will get the summation of half mr squared omega squared. And the omega squared can be factored out because every particle has the same angular velocity in an object. And the summation of m times r squared is defined as the moment of inertia, and you can replace that part of the equation with I. And so the equation for the rotational kinetic energy becomes I omega squared.
These are a few equations in rotational motion, but they're pretty intuitive if you know what to replace them with. Because the equations in rotational motion are exactly like their corresponding equations in linear motion, except they're the angular versions of their values. For instance, x distance is replaced with theta, angular distance. V, velocity, is replaced with omega, angular velocity. A, acceleration, is replaced with alpha, angular acceleration, which, by the way, is not to be mistaken with radial and tangential acceleration. Angular acceleration is change in omega over change in time, whereas tangential acceleration is change in velocity over change in time. And radial acceleration is v squared over r. Then the force F is replaced by tau, torque. Kinetic energy, K, is replaced by radial kinetic energy, rotational kinetic energy. And mass is replaced by moment of inertia, I. And momentum, P, is replaced by L, angular momentum. So these are a lot of equations that are useful when calculating for rotational motion, but they're not anything new to be memorized because they're the same old equations, except they're based on angles instead of distance.
Questions.
Consider an oxygen molecule rotating in air. The mass of each oxygen atom is 2.66 times 10 to the negative 26 kilograms. The radius is 0.5105 times 10 to the negative 10 kilograms. A. Calculate the moment of inertia. B. If the angular speed is 4.6 times 10 to the 12th radians per second, what is the rotational kinetic energy?
Now take this moment of silence and answer your questions. Questions! The quantities
I and omega are analogous to what in linear motion?
Now take this time and answer your question.
You must answer these questions correctly.
Write down the four kinetic equations in rotational motion. Now take this time and write down your answer.